All right, so welcome to the second Teacher Scholar Lecture, March 18, 2020. And what I want to do today is I want to talk about error correcting and error detecting codes. Okay, is everybody able to see the slides?
Yes.
Okay, everything look good? Yep.
Yep, I can see it.
I'm sorry?
Yes.
Okay, everybody can read it?
No, of course not.
So this is a talk I gave not at MothFest, but at MathFest back in the time when we were actually allowed to fly and travel to places. As a humorous remark, when I submitted the title and abstract, they thought that there were some typos and they fixed it. And then after they fixed it, they emailed me, oh, wait a minute, you probably meant it to be spelled like that. So if you look at this spelling, most of it should not be too hard for you to process in real time as to what is meant. And so what I want to talk about now is error detection. How can you tell if something has been mistransmitted? And error correcting. Given that it was mistransmitted, can you fix it? All right, so as you would guess, this is what the talk should be titled. Okay, so introduction. So instead of sending letters, it's enough to just send zeros and ones. So computers love to work in binary, on, yes, no, true, false. And so if we use blocks of 5, that gives us 32 possibilities, because 2 to the 5th is 32. So we could make an A be all zeros, a B be 0, 0, 0, 0, 1, and so on and so on and so on. If you wanted to have a little bit more, you could do blocks of 6, and then you could get up to 64. You could have all your letters. You could have a symbol maybe meaning uppercase what follows. You could have punctuation marks. You could have numbers. And the two big issues in all of what we do is we want to transmit messages so that only the desired recipient can read. And the next is to ensure that the correct message is received. So one of the things that's nice is we actually have 2 classes with each other. So if people are interested, I can teach you RSA encryption. How do you transmit messages so that we believe only the desired recipient can receive and decipher it? There are better methods now than RSA. We cannot prove that RSA is secure, but in order to break it, you need to be able to factor large numbers quickly, which to date nobody knows how to do. The mathematics you need to use it is, for the most part, doable with just basic algebra. So I have actually taught this in the elementary school to some of the more advanced and math-interested students, just as an after-school project going over several weeks. And so if people want to, that'd be a really nice set of lectures of things we can do. And then depending on the background of your students, there's of course many different ways you can push it. For today, however, I want to concentrate on making sure the correct message is received. All right. Any Futurama fans? The makers of The Simpsons. This is one of my favorite moments. And so they see this number that looks like it's in binary, written in blood, and they ask the robot, what does this mean? Because the robot speaks binary, and he goes, I have no idea. Later in the episode, the robot sees this number reflected in a mirror and starts running away screaming. It's the number 666, the number of the beast, written in binary backwards. So somebody just asked about seeing the whole image. Unfortunately, that's all of the image that I posted. So the image is deliberately cut off a little bit to just try to make the one as large as possible. They go to tremendous lengths to have great math jokes in it. There's some ones with the Harlem Globetrotters who turn out to know a tremendous amount of advanced mathematics. If anybody wants to, I'm happy to later talk about some other great math moments in the series and some great math games you can do. Okay, so we're not going to do RSA now, but I'm going to just give you a quick sketch of how RSA works so you can try to decide if you want to learn more about it. So the way it works is you choose 2 secret primes. Normally they have about 200 to 400 digits. I'm going to choose smaller ones, P and Q. You choose the number D, which is secret. You make public N, which is the product of P and Q. And you make public some number E. And you have to choose these numbers such that when you take ED and you subtract 1, it's a multiple of P minus 1 and Q minus 1. You then take your message M, and you have to send M to the eth power mod n. So what this means is you look at the remainder when you divide by n, And then to decrypt, you take the message you received, you raise it to the dth power, and you look at the remainder when you divide by n, and that turns out to be the message. So why all this works is some tremendous mathematics, but we can do it for the most part just using algebra 1. Now imagine if instead of receiving 12120947 we received 12120948. We just had a 1-bit transmission error. When we try to decrypt it, instead of getting 1956324041, we have something that's not even close. That's one of the powers of RSAs. Because we encrypt the whole message together and mash it all together, any small error is going to make it essentially worthless for the recipient. Now, since we have 10-digit numbers, I always like to talk about what do we expect to work. Well, I would expect if I have 2 random messages that 1 out of every 10 digits will just naturally align. And so if I took this message and I just wrote down something at random, I would expect to have about 1 digit correct. And if you look over here, we have 2 digits right, but we only have 2, 4, 6, 8, 9 digits. It's not unreasonable. This is the opportunity to talk about small data sets. So anybody know any great events from the year 2004?
Probably the Boston Red Sox World Series.
Yeah, what a wonderful event to talk about, the Red Sox World Series victory.
Great event.
And so, I'm sorry, this is just what I was naturally going to talk about. And so before the Red Sox had done that, no team had ever come back down 3-0 in a best-of-7 series in baseball. They had in basketball and hockey, but not in baseball. But it had only happened a little bit over 20 times. And if the 2 teams are equal, how many times would you have to play before a team comes back down 3-0? Once every how many times? What would you guess? If the 2 teams are equal, what's your probability of winning 4 games in a row?
0.5 to the power of 4.
Right, so 1/16. So we've only had it happen on the order of like 25 times, so you would only have expected once or twice a team to come back. So the fact that no team had ever done it before the Red Sox, it's not that surprising. Also, there might be a reason why teams aren't coming back down 3-0. Can you give me a reason why they might not be coming back?
They're not the Yankees.
That's one reason. So what would be true about, for the most part, when the Yankees are beating a team 3-0? Why might the Yankees be beating them? The Yankees are?
Lucky.
I would prefer lucky. Unfortunately, the mathematics suggests better is the right answer. Is that there's a reason why you're down 3-0. The other team is possibly better than you. So we're going to concentrate on error detection and error correction. So the first method we're going to talk about is the check digit method. And then we're going to go on to majority rules and generalization. So how many of you have heard of check digit? Okay, so if it's easy to read again, we don't need to be able to correct the error. We just need to be able to detect the error. So I haven't checked the news from the day. I think we're still allowed to go to supermarkets. So supermarkets have scanners. And the scanner is one of the greatest inventions in the 20th century. What it does is the clerk no longer needs to know the price of items. Also, as soon as you buy something, it can update the store's inventory immediately. It can also look and correlate purchases. Oh, you bought this, and this, and this, and this, and this, and this. This is one of the reasons why they have you get the store cards and they give you this discount. They want to look at your correlated purchases. There was a wonderful story a couple of years ago from a Target, I think in Minnesota, where they sent some coupons to a household and the father storms in and yells at the manager because they got all these pregnancy coupons and he and his wife are way too young, and his high school daughter and junior high son are way too young. And the manager is very apologetic. He gives him some gift cards. And then a few days later, the manager calls up to just check it and see how things are going. And the father is a little bit sheepish and has to admit that there are some extracurricular activities his daughter was engaged in that he was not aware of, and those pregnancy coupons will be useful after all. So Target knew before he did that there was a baby expected in the household. And they were able to do this correlations. Now, I find it a little bit upset that you're mad that you're being targeted by a store that's called Target. But Target wanted to continue to mine the data on people, but they just didn't want people to know that they were doing it. And so the solution they came up with was absolutely brilliant. What they did is they still want to make sure that they send these coupons, because if you see these coupons, that might increase your probability of going to Target. If you have a little kid, one-stop shopping, that's real convenient. What they did is they would make sure they put in some coupons that were anti-correlated with who you were. So it looks like it's a random selection of coupons. So rather than giving things that just look like they are appealing to you, they instead give you a wider swath so that it doesn't seem like they are deliberately targeting you. So in a supermarket, if you have a scanner, if it doesn't scan correctly, what happens?
Beeps.
I'm sorry?
It beeps.
It beeps, and then you get upset and you get into a fist fight with the, right? No, they just scan it again. It's not a big deal. And so all you need to be able to do is detect that an error was made. So I'll do it two different ways. The first is using numbers base 10. The second is just using numbers base 2. And what we're going to do is we're going to choose the last digit in blue to be the number such that the sum is a multiple of 10 for the top or a multiple of 2 for the bottom. So I'm always going to use red or pink for my data digits and blue for my check digits. So 9134, that adds up to 17. So if I put in a 3, it's going to add up to 20, a multiple of 10. 1101 adds up to 3. So if I put in a 1, it adds up to a multiple of 2. And so I'm adding one extra. And this is a really good test, because now imagine I receive the following. Is it possible that the bottom could be correct? 11010. Does that sum to an even number?
No.
No. And the top, does the top sum to a multiple of 10?
Yes.
No.
No.
It sums to 21.
Yeah.
I know there's a mistake. Now, if we were assuming that these are the correct data digits, you can see I changed the second one in the first line to a 2, and I changed the last one in the second line to a 0. So in the first case, the error was actually in one of the digits that mattered. In the second case, annoyingly, you transmitted the message correctly. It was the check digit that was wrong. In neither case do we know where the error is. We just know an error was made. And from that, we then know we have to check again. We have to have it scanned again. There's more involved methods you can use. I've got a link here to some more elaborate systems that allow you to detect different types of errors. What if you flip the order of 2 digits? You're typing on a keyboard. If you flip the order of 2 digits, that's never going to be detected by this method. But it's not enough to just detect the error in general. You want to be able to know where the error is. Are there any Seinfeld fans here?
Yes.
Yes.
Oh, yes.
Okay, so if I give you the word loser, who do you think of?
George,
George.
Yeah, George Costanza. He's the poster child for being a loser.
he's a Yankee fan too.
Not only is he a Yankee fan, he actually worked for the
He's
Yankees.
an employee, yeah.
Yep.
An employee. In what I think might be the greatest episode of Seinfeld, called The Opposite, he is bemoaning how he has never made a right decision in his life. Any time he's had a choice to make, he's always made the wrong one. So they convince him that he should just do the opposite of his instincts. So it starts off, he sees an attractive woman at the restaurant who's smiling at him. And so he goes over and she says, you ordered the exact same thing I did. He eventually then meets George Steinbrenner as he's being interviewed for a job. And Steinbrenner says, it's nice to meet you. And he responds, I wish I could say to you. And then just cuts loose. If you had to choose a percent for success, what would you like your success rate to be?
100.
100%. Now imagine we're transmitting information. We're transmitting zeros and ones. If we transmit with 100% success, will the receiver get the correct message? 100% successful in each digit you transmit. Will they receive the correct message?
Yeah.
What is the worst success rate to have in transmitting a message?
0.
No, think of George Costanza. Imagine your success rate is 0 and there's only 2 options. If you are always wrong, what should the receiver do?
Just assume the opposite.
Assume the opposite. So if you have a 0% success rate, and we know that, it's actually as good as being 100% successful. What's the worst success rate?
So 50.
50%. Because if it's 50%, it's as likely to be one or the other. So we want to detect where the error is. So the simplest method is tell me twice. So you promise that you will only transmit 1, 1 or 0, 0. And if it's rare to make an error, it's unlikely that we will get both digits wrong. And so if you receive a 1, 0 or a 0, 1, you know a mistake was made. Has to have been a mistake. If you receive a 1, 1, is it possible both digits are wrong? It's possible, but it's unlikely. If we're in a situation where we have such a high rate of error, we can't really communicate. So we have to assume that most digits are successfully transmitted. If you want, think of it as you're transmitting message and maybe every now and then there's a solar flare or something and that's going to disrupt the message, but most of the time the digits are going to get through. How much of your message is information in this case? So if we're transmitting 1, 1 or 0, 0, what fraction of the dots are pink?
1/2.
1/2. So half of the message is information, half of the message is error detection. So majority rules is an even better way in some sense. We can transmit everything 3 times, 1, 1, 1 or 0, 0, 0. Why is this good?
Majority rules.
Majority rules. So if I give you now 1, 0, 1 or 1, 0, 0, what would you say the first message was probably?
1.
Yeah, it was probably, I probably meant to transmit 1. And the second message, what do you think I meant to transmit?
0.
0. So the nice thing is this allows us to not only detect errors, but actually correct errors. How much of our message is actually the information we want to transmit now? What fraction? So what fraction of the message is the data and what fraction is the checked digits?
2/3.
So 2/3 is which one? The checked digits or the information?
I don't know.
The check digits.
So the blue is the checked digits. So we have 2 checked digits and we have 1 piece of data. So the fraction of the message that's data is just 1/3. So is this good or bad? So what do you think? Give me some positives, give me some negatives. Is there anything positive you can say about this method?
The data is the same?
What do you mean by the data is the same?
So your pink digits are the same in both cases?
Well, that just happens to be the example I'm giving you.
Okay.
So in this example, I can detect and fix a 1-bit error, a 1-digit error. So if 1 digit is wrong, this method will not only detect it, but will tell you where the error is. So to me, that's a real positive, that it does more than just detect the error. It tells you where the error is and how to fix it. The problem is it's expensive. only 1/3 of what we transmit is the actual information. If you are old like I am, you remember the dial-up modems. The dial-up modems, it was extremely frustrating at times. It seems to actually be what the internet is like today. We've gone back in time. And now we have wait times to download pages. So the more information you can transmit, the better. And so there's trade-offs. And what I like about this when you're talking to students is there are trade-offs in life. What's best? Well, it depends. For some things, this is better. For some things, this is worse. And so, there's some stuff that we can use. As I mentioned, only 1/3 is information. So the question is, how could we do better? Well, we started off with tell me twice. We then did tell me 3 times. What could we do after tell me 3 times?
4?
Yeah, tell me 4 times. Unfortunately, this makes things even worse. So now only 1/4 of the message is data, but now you're much more likely to detect a real error and not have a false. So when we told me 3 times, it is possible that 2 digits are flipped. It is much less likely that 3 digits would be flipped here. And so you can be more confident about what you receive. The problem is you have even less data being transmitted. So perhaps for the hotline between the US and the Soviet Union, this might be a situation where we are really concerned about making sure the correct message is received. And if we have good bandwidth, we may not be so concerned about losing 75% of our message to checking digits. But maybe there's a better way to do things. And so what I like about this problem, and I've done this with the elementary school kids, is that you can start to think about other ways to do better. Different metrics, different measures of success will make one measure better than another. And the other thing is we have to define what we mean by a success. So for me, I would like greater than 50% of the message to be data, and I still want to be able to correct 1 bit that's wrong. To me, psychologically, it feels good if more than half is data. Less than half doesn't feel so good. So here's another way to look at tell me 3 times. I'm just rearranging the geometry. So this now becomes a geometry talk. So the pink digit is always going to be the message I care about, and the blue is the check digits. So in both of these cases, I have 1 data point, and I have 2 check digits. How about 2 data points? Does anybody have any thoughts as to how you would do 2 data points geometrically? So we could have a long line.
Pink, blue, pink.
So we could do pink, blue, pink, but that would be 1 check digit.
Oh.
Do a rectangle.
So maybe like some kind of like a rectangle or something. So here, one way to look at it is I'm going to have a check digit here to make this row have an even sum. And I'm going to have a check digit here to make this column have an even sum. And so if I do it like this, I want this to be a check digit for this row, and these to be check digits for the columns. So now 2 out of 5, or 40% of the message is data. So imagine that this pink digit was wrong. We transmitted it wrong and everything else was transmitted correctly. Because this is wrong, this blue check digit is going to indicate there's something wrong in this row. This blue check digit will say everything is okay with this row, and this blue digit would say there's something wrong in this, this column, and this blue check digit would say there's something wrong in this column. So we know there's something wrong in this column, there's something wrong in this row, the mistake must be this digit here. So if there is an error in this one spot, these 2 check digits would indicate its location. If there was an error just in this check digit, then these 2 column checks would be okay, and I would know that the error is there. Look at every single case, and you can see that this will detect and correct any 1-bit error. And 40% of your message. So now we would go up from 2 bits of data to 3 bits of data. Any thoughts as to what shape we might be able to do with 3 points? So what kind of shape could you make with 3 points?
Triangle.
A triangle. So here's a way to do a triangle. And I'll put check digits at the ends. So now imagine that this pink dot is wrong. Then this check digit indicates there's something wrong with this line. This check digit would indicate there's something wrong with this line. And this check digit would say it's fine in this line. So the unique point that intersects these 2 lines is right here. And you can go through all of these cases. And you can see that half of your message is now data. I could also do things with a square and 4 data points and 4 check digit points. Which do you think is better, the square or the triangle?
Triangle.
Why the triangle?
Actually, no, the square, the other one, because there's more directions.
But they both have a 50% efficiency. They both transmit 50% of the message as the data you care about.
Then I don't know.
I think the square is definitely easier for us to visualize, to encode, and to generalize.
Does it also take up less space?
So the triangle takes up less space. I can transmit, the more digits I transmit, the more likely it is that there's going to be 2 errors. So with the triangle, I can actually transmit 50% using smaller blocks. So I would give the tip of the hat to the triangle. It's easier to code the square, but you only have to code it once. And now the question is, what should we try next? 5, 6, 7, 8, 9? Anybody know what might be a nice number to try next?
If you want to stick with the triangles, 9.
So if we try a triangle, so how many data points do you want?
6.
So 6 data points, maybe make a bigger triangle. And if we wanted to do the next square, what would the next square be?
9.
9.
So maybe some numbers like 6 and 9 are actually good numbers to try next, but maybe 5, 7, and 8 might not be so good. But the number of data points you have is going to lead to different geometries. Here, it's not that bad to do a square. Now I have 3 rows, 3 columns. For the triangle, here is one way to do 6 data points for a triangle. And I've got my lines, and I add 1 new check digit, which is coming from this circle from those 3. So if you play the games for a little bit, you will see that in both cases, if there's one and only one error, it will be uniquely determined. So for instance, if it's this pink dot on the bottom, then this blue check digit will have an error, this line will have an error, and the only intersection is here. Now, here's another way of drawing the triangle. If you look at this way, you can see it's very similar to what I did here. I just changed those blues to new check digits and then added a new check digit, and I continued the line, and then I drew a new line connecting those. So that there is another way to try to draw this in a natural way where you add new lines and you extend the previous lines. But the square is easier to work with. If you want to look at the efficiency of each, you want to see what fractions. You count how many data points do you have and how many check digit points do you have. And you can see, it's nice that we talked about dimension earlier today, that the boundary, at least for the square, it's very easy to see, is growing linearly in n, while the number of data is growing like n squared. So in the limit, we're going to have almost 100% being transmitted. And so for the square, you can actually do the calculation, you get n over n plus 2, so a very high fraction. So if we take n equals 2, we get 50%. If we take n equals 3, we get 60%, so we break that 50%. So we can already at least make me happy. All right, so we can get as high of a percentage as we want, but we're going to have to use longer and longer strings. And we want to get a high percentage without using a huge number of strings. All right, so what's a better geometry to use? So I'm not going to go into too much detail on this, You could use Rubik's Cubes. You could go three-dimensional. And then what you would have to do, you have the geometry of faces now. So I know some kids love algebra, some kids love geometry, lots of different ways you can do this. And again, happy to chat about stuff like this later. I'm not going to go through all the details of the calculations. There's lots of different types of Rubik's Cubes you can do. I love Rubik's Cubes, where you can do stuff like this where maybe this center is going to be a check digit. And then these are all your data digits. And then you can see which things lie on. So there's a lot of great geometry you can do. You can use the Platonic solids, and you can ask students, what could you do? I'm not going to go into detail on the Hamming codes. Hamming was the scientist who's responsible for a lot of the advances in the subject. He is the one who remarked, if the computer can detect that there's an error, why can't it correct the error, except to use stronger language? And here is a way to set up an error-correcting, error-detecting code where you have 7 digits, and 4 of the digits are data, and only 3, the blue, the orange, and the green, like subway lines, are the check digits. So this one is the check digit. You take 5, 6, 7, and 4, and you want that sum to be a multiple of 2. Here you would want 3, 6, 7, and 2 to be a multiple of 2. And you can just go through the calculation and see that it works. The question why it works is a little bit more involved. Happy to talk about that later if there's interest. It comes down to using binary. What's really going on is 7 is 1 less than a power of 2. If you want to see how well the various things do, if we wanted to transmit, say, around 4,000 bits of data, the square would give us a 96.9% effective rate. The cube would give us 98.8, and the Hamming code would give us about 99.7. So at this point, they're all doing extremely well. But there are efficiencies that can be gained. The last one I want to mention about transmitting is this wonderful idea of interleaving. So I learned about this from my brother, and the idea is there's often very simple things you can do in life that can make a tremendous difference. So imagine we're transmitting a string of zeros and ones and there's a burst of noise. If there's a burst of noise, then the error is probably localized. And so if we now transmit this in different blocks, it is likely that we have more than one error in one of our blocks. And the idea of interleaving is we'll just do every 4th, but you might really do every 100 or every 1,000, is split your string and transmit every 4th. So now if you have that burst, it now spreads it onto different strings. And now you're back in a case where it's unlikely that you would have multiple errors together. So this is a great example of how a really simple idea can have incredible applications. So for the last few minutes, I want to talk about hiding images. So this is the subject of steganography. So I will be shocked. Is anybody able to see the cat hiding in the tree?
No.
So the cat is there. Let me talk to you about how you would transmit an image. So we normally have a length by width grid. So we would have L times W pixels. And each pixel is a triple, maybe red, green, blue. And we often associate, a value to each going from 0 to typically 255. So there's a little bit over 16 million possibilities. For me, I can't really see 16 million different shades of colors. If you do 8 reds, 8 greens, 8 blues, that's probably more than enough for what my eye can handle. So this gives us an opportunity. So take one of the colors red. And so rather than writing numbers in decimal in base 10, we're going to write numbers in binary. So the number can be written from 0 to 255. So here's the 1's place, the 2's place, the 4's place, the 2 to the 6th place, the 2 to the 7th place. If we just change the last or the last 2 digits, we're not going to change it by that much. We're going to change it by at most either, 1 or maybe 3 out of 255. Percentage-wise, that's small. What we can do is we can hide an image in an image. So imagine I have a text, a message I want to send to somebody in secret, and I have black letters on a white background. Well, each pixel will either be a 0 if it's black or 1 if it's white. And then what I do is I change the last digit of red to be whatever pixel I want for that message. If I want to send something in color, I can change maybe the last 2 digits, and then that would give me 4 reds. If I do the last 2 digits of the green and the last 2 digits of blue, I would get 4 cubed or 64 colors. So by just changing the last 2 digits, I can actually embed a low resolution image with 64 colors in a higher resolution image. So here is the tree, there is the cat in the tree. And it was done by just changing pixel by pixel by pixel. All right, so what I thought we would do now is I'm going to, let's see, we have 3 minutes left, so I'll see if there's any quick questions about stuff we've done now. Then we'll take a break and then assess what to do next. So any quick questions about the content? So what's nice about this is it has tremendous applications to the real world. You know, we, especially now that physical classes and social distancing are coming in, we are going to be doing far more online than we've been doing before. And we need to make sure that we're transmitting things correctly. If you're downloading a 2 GB file, you don't want to download the whole thing and then find out that there was an error. Or if you're a sub off C, you might surface at a key moment in time to receive message from headquarters and then resubmerge. You can't ask them to retransmit. You have one shot. And so the question is, how can we transmit stuff like this and be sure that the receiver, the recipient, gets the intended message? Once we start thinking about this, we see that depending on the geometry we choose, there are different ways of looking at the same problem, and some extend better than others. It's also natural to just be constricted in how you're looking at things. We're doing things on a line, we're doing things in a plane. Well, let's expand to 3 dimensions. Let's look at what's going on with a cube, or maybe some other shapes, some platonic solids. What would happen if we went up to 4 dimensions? Are there other savings that we could get? And so for me, when I do this with students, the big thing is always trying to get them to be creative. What would you like to try to guess? How would you try to extend this? All right, so it is 11:21 right now. Let's resume in 5 minutes at 11:26. All right, have a good one all.